Hello everyone. In this lecture, I would like to discuss one of the important topics in mathematical physics, which is determinants. A determinant is a square array of quantities, each called elements, which may be combined together according to specific rules. In simple form, a determinant D is equal to, this is the symbol for determinant, A11, A12, A13 until A1n. The first one here is the row and the second one here is the column. So 1, 2 here, it means first row, second column. 1, 3 means first row, third column, and so on. A21, A22, A2n. You keep going this way until you have AN1, ANN. Again, it has to be square, so number of rows equal number of columns. Now the value of the determinant in terms of elements A11, A12, and so on is defined as D equal to summation I, J, K, R, epsilon I, J, K, R, AI1, A, J2, A, K3 until ARN. So the upper limit for the summation, it's n. In such a way, epsilon I, J, K, R equal to, it's either +1 for even permutation. We will discuss this in a moment. -1 for odd permutation. And 0 for any repeated index. This epsilon here is known as Levi-Civita symbol. To understand this even permutation and odd permutations, let's have this case assuming that we have three numbers, 1, 2, and 3. In this case here, epsilon ijk, it's either +1 if ijk equal to 1, 2, 3. It's cyclic, or 3, 1, 2, or 2, 3, 1, and so on. So remember, after 1 it's 2, after 2 it's 3, after 3 it's 1. Now after 3 it's 1, and after 1 it's 2, and so on. Now -1 if ijk equal to 1, 3, 2, and so on. 0 if ijk equal to repeated index. So 1, 1, 2, 2, 2, 3, 3, 3, 1, and so on. A second order determinant, and in this case it's equal to, is defined as D equal to A11, A12, A21, A22. Remember, A11, it means first row, first column, and A21, it means second row, first column, and this one here, it means second row, second column. Using this rule to find the value for this determinant, D in this case will be equal to summation, and we have here only two indices, I and j, and n it's 2, epsilon ij, a I1, a j2, or we can say that summation over j. Let's solve it for I first, then solve it for j. 2 epsilon, the first value for I, it's 1, j, a, 1, 1, a, j, 2, plus epsilon 2j, a 2, 1, a, j, 2. Now solve it for j from 1 to 2. You will get here epsilon 1, 1, a 1, 1, a 1, 2, plus epsilon 1, 2, a 1, 1, a 2, 2, plus epsilon 2, 1, a 2, 1, a 1, 2, plus epsilon 2, 2, a 2, 1, a 2, 2. Now this first one here, because of the repeated index here, so this one will be 0, and because of the repeated index 2 in this case, this one will be 0 as well. Now in this one here, it's 1, 2, in this case it's positive, and this one here 2, 1, in this case it's negative. So you will get 0 plus a 1, 1, a 2, 2, minus a 2, 1, a 1, 2, plus 0. So the determinant after all will be equal to a 1, 1, a 2, 2, minus a 2, 1, a 1, 2. Now let's apply the same rule, this one here, for third order determinant. So an n in this case, it's equal to 3. I just copy it here. Now let's apply this equation here for a third order determinant, n equal to 3. Therefore, the determinant, it's equal to a11, a12, a13, a21, a22, a23, a31, a32, a33. Now to find the magnitude for the determinant, let's use this equation right here. So D in this case equal to epsilon 1, 2, 3, a1, 1, a2, 2, a3, 3, plus epsilon 1, 3, 2, a1, 1, a3, 2, a2, 3, plus epsilon 2, 1, 3, a2, 1, a1, 2, a3, 3, plus epsilon 3, 1, 2, a3, 1, a1, 2, a2, 3, plus epsilon 231 A21 A32 A1 3 plus epsilon 321 A31 A22 A1 3. After simplifying this one here, and remember the Levi-Civita rule, this one here, if you have even permutations, you will have positive 1, odd permutations, you'll have negative 1, and if you have a repeated index, you will get 0. D, after all, will be equal to A11, A22, A33, and this one here, right here, it's 1, positive 1, because it's even pair permutation, minus A11, A32, A23, minus A21, A12, A33, plus A31, A12, A23, plus A21, A32, A13, minus A31, A22, A13. Remember, the positive because of even permutation and the negative because of the odd permutation. And simply we can rewrite this one here, D, as A11 and times A22, A23, A32, A33, minus A12, 2 by 2 determinant here, A21, A23, A31, A33, plus A13, A21, A22, A31, A32. Remember, if we take A11 as a common factor here, you will get A22, A33, this with this, minus A32, A23, which is this with this. Same thing applies here, and same thing applies here as well. As we can see here, a determinant of order 3 can be defined as a determinant of order 2, and in the same manner, a determinant of order 4 can be defined as a determinant of order 3, and as a generalization, a determinant of order n can be defined in terms of a determinant of order n minus 1. Therefore, let's write the general solution for a determinant of order n. In this case here, D equal to A11 M11 minus A12 M12 plus minus 1 to the power 1 plus j A1j M1j plus minus 1 plus n A1n M1n. And this is as a generalization for the value of a determinant of order n. In such a way, M1J here is a determinant of order n minus 1. And it's called the minor of element A1J. This is called here the minor of A1J. And minus 1 to the power 1 plus j, M1J is called the cofactor of element A1J. Generally speaking, minus 1 to the power I plus j, Mij, is called cofactor of element Aij, and can be obtained from the original determinant by covering or deleting the ith row and the jth column and introducing the sign minus 1 to the power I plus j on front of the new determinant. To understand this very well, let's have this example. In this example, the minor corresponding to the element 2 in the third row and second column of the fourth order determinant. So this is the fourth order determinant, and we would like to find the minor that corresponds to the element 2 in the third row. This is the third row right here. This is the third row. And second column, this is the second column. If we cover this and cover this, the rest will be the minor. So in this case here, the minor will be 3 by 3 determinant, and it should be 7, 3, 1, 5, 6, 3, 8, 1, 6. And to find the cofactor in this case here, just place in front of this determinant here minus 1 to the power I plus j. So in this case, it will be minus 1. Now remember, third row, so I is equal to 3, and second column, j equal to 2. So 3 plus 2, it's 5 here, and you multiply it with the minor, this here, 7, 3, 1, 5, 6, 3, 8, 1, 6, and this will be equal to minus 1 to the power 5. It's minus 1 times this one right here, 7, 3, 1, 5, 6, 3, 8, 1, 6. Now, as a generalization, and we would like to use, instead of using the first row, we would like to use the ith row. In this case here, the determinant D, it's equal to minus 1 I plus 1 AI1 MI1 plus minus 1 to the power I plus 2 A12 MI2 until minus 1 to the power I plus j Aij Mij plus minus 1 I plus n, a, I n, m, I n. In compact form, we can write d, this one here, equal to summation j equal to 1 to n minus 1 I plus j a I j m I j, or equal to summation a I j c I j, in such a way the cofactor Cij is given by minus 1 I plus j mij. Now in the same manner, d will be equal to summation minus 1 to the power I plus j a I j m I j I from 1 to n, which equal to summation a I j c I j I equal to 1 to n. And this is called Laplace development by minors. Example: use Laplace development to evaluate the determinant, this one here, and this one's 4 by 4 determinant. Now to use Laplace development, d will be equal to minus 1. We can pick up any row or any column, but the good thing here is the third column, this one here, most of the elements 0. So if we pick up the third column, this will make things much easier for calculating the determinant. So let's pick up the third column. Now it doesn't matter actually for the which row you pick up. So let's pick up the first row. So using the first row and third column, so the cofactor here, it's 1 plus 3 because first row and third column, and the common factor here, it's minus 3 times the rest of the determinants will be minus 5, 6, minus 2, 0, 2, 4, 0, 5, minus 4. Now let's downsize the 3 by 3 determinant by using Laplace development by minors. In this case, d will be equal to minus 1 to the power 1 plus 3. I'll just drag it down as is. Now pick up any column or any row. As we can see here, the column number 1 has more zeros, which makes things much easier to calculate here. We will see later on in the properties of the determinants. So let's choose the first column and the first row. Again, minus 1, first column, first row, so 1 plus 1 times the common element between the first row and the first column, it's minus 5 times the rest, 2 by 2 determinant, which is 2, 4, 5, minus 4. Upon simplifying this, minus 1 to the power 4 is just 1. So minus 3, minus 1 to the power 2, it's 1, times minus 5, just leave it as is. Now this with this minus this with this. So minus 4 times 2, it's minus 8 minus 20. So minus 8 minus 20. So the answer will be 15 times 28, which is minus 420. One more example. Evaluate the determinant. This determinant right here. D in this case, it's equal to minus 1. Now pick up any row and any column. Now the good thing is to choose the one with more zeros. So the first row has more zeros in this case here, and the first column. So 1 plus 1. Now the common element upon hiding the first row and hiding the first column, it's A times the rest, B06C, B06C, and the answer will be D here, equal to minus 1 to the power 2 is just 1, A, now B, C, and this one 0. So the determinant here is A, B, C. Now let's discuss the properties of determinants. The first property here, the interchange of any two rows or any two columns in a determinant changes the sign of the determinant. So this property is called the anti-symmetry property. Example, if we have this determinant and this one here, and we just switch the first column, this one here, and make it as the second column, and replace the second column and make it the first column. After doing this procedure, you will get 2, 4, minus 1, 1, 3, 5, 3, 3, 2. Now this determinant equal to this determinant with minus sign. The value for this determinant, it's equal to the same value here with negative sign. Same thing if we exchange the, for instance, the first row with the third row. So we move this one here and we move this one here. So the new determinant will be this one here, and again the value for this determinant will be the same with minus sign. So this is actually the first property of determinants. The second property of determinants, if two rows or two columns in a determinant are identical, then the value for the determinant is 0. So second property here, example, this determinant here, we have the first row, this one here, is identical to the third row. For this case, this is D. The value for this D is equal to 0. And in this determinant here, as we can see here, the first column is identical to the third column. The value for this determinant is equal to 0 as well. So if we have two identical rows or two identical columns, the value for the determinant is equal to 0. Now the third property of determinants, if a row or column is multiplied by a certain factor, then the value of the determinant is multiplied by the same factor. Example, we can see that the first column, this one right here, is actually multiplied by 2. So we can state that the value for this determinant, it's equal to the factor 2 multiplied by 1, 2, 4, 1 minus 1, 3, 2, 0, 2. Now let's move to the fourth property of determinants. If two rows or two columns are proportional, then the value of the determinant vanishes. Now we can actually use the property 2 and property 3 of determinants, this and this. Now the property 2 states that if two rows or two columns are identical, then the determinant equal to 0. And the third property, if a certain row or column is multiplied by a certain factor, then the value of the determinant is multiplied by the same factor. So if we look at this determinant here, we can tell that column number 1 is actually proportional to column number 2. Now if we take 2 out of the determinant, so it will be equal to 2 times 1, 2, 4, 1, 2, 4, minus 1, 0, 1. By looking to the new determinant here, you will see two columns are identical, then the value for this whole determinant will be equal to 0. And same thing here applies if two rows are proportional to each other. Now let's move to property number 5. If each element in a row or column is equal to 0, then the value for the determinant vanishes. And this is actually pretty simple one. As an example here, by looking to this determinant here, we can see that all elements of the first column are zeros. In this case here, if we use the Laplace development and choose, for instance, for the first element is the first row here and first column, and for the second one use the first column and second row, and the third one is the third column, third row. So this is multiplied by 0, 0, 0. So the value for this whole determinant is actually equal to 0. Again, this applies if each element of a row equal to 0. Then the value of the determinant will vanish. Now, property number 6, if every element in a row or column can be written as the sum of two terms, then the determinant can be written as the sum of two determinants. Example, now 6 here. If we have a determinant a1, 1 plus D1 1, A2 1 plus D2 1, A3 1 plus D3 1, A1 2, A2 2, A3 2, A1 3, A2 3, A3 3. We can rewrite this determinant as the sum of two separate determinants, which equal to this one here, A1 1, A2 1, A3 1, and same as in this one here, A1 2, A2 2, A3 2, A1 3, A2 3, A3 3, plus now D1 1, D2 1, D3 1 with the same elements right here. So D1 1, D2 1, D3 1, A1 2, A2 2, A3 2, A1 3, A2 3, A3 3. Property number 7, adding the multiple of a row or column to another row or column does not change the value of the determinant. As an example, we have here a determinant D, it's 1, 2, 4, 5. If we add to row number 2, 2 multiplied by row 1, in other words, D equal to 1, 2, and you would like to add double row 1 to row 2. So 4 plus 2 times 1 and 5 plus 2 times 2. This new determinant will be equal to 1, 2, and this one here 6, and this one here 9. If we find the value for this new determinant, it will be equal to 9 times 1, it's 9, minus 12, it's minus 3. And if we find the value for the original determinant here, it's 5 times 1, it's 5, minus 8, it's minus 3 as well. So the value of the determinant does not change if we add the multiple of a row to another row or column. Now, property number 8, the value of the determinant does not change if all rows and columns are interchanged, which means if we have a determinant like this one here, and we just changed all rows or all columns and modify their position, so make, for instance, row number 1 make it row number 2, and 2 make it 3, 3 make it 1, and so on, and we interchange all rows. In this case, as an example here, let's see, 5 for 1, 1, 2, 3, 3, 2, 5. As we can see here, row number 3 becomes row number 1, and row number 1 becomes number 2, and row number 2 becomes row number 3. In this case here, the value of the determinant does not change. it will change back to the properties before. It will change if two rows or two columns interchange. But if we interchange all the elements, all the columns, or all the rows, the value will be the same. Now, property number 9, if each element in the determinant of order n is a function of x, then the derivative of the determinant with respect to x, for instance, is the sum of n determinants obtained from D by differentiating each row or column in turn. Example, if we would like to derive this determinant right here, let's first derive the first row and keep the other rows as is, plus derive the second row and keep the first and third row as is, plus derive the third row and keep the first and second rows as well. So this is the derivative for a determinant, how it works. Now let's learn how to multiply two determinants. Let's have an example. If we have a determinant A, this one right here, and determinant B, this one right here, we would like to find the determinant C, which equal to A multiplied by B. Now, to multiply two determinants, let's follow this technique. You multiply the first element of this row with the first element with this row, plus the second element of the first row with the second element of the first row, and the third element of the first row multiplied by the third element of the first row, and the result will be 2 multiplied by 7, it's 14, plus 5 times minus 2, it's minus 10, plus minus 1 times 1, it's minus 1. So this is the first element of the new determinant. Now, as the second element, let's multiply the first row with the second row. The same rule here. 2 multiplied by minus 3, it's minus 6. 5 multiplied by 2, it's plus 10. Minus 1 times 2, minus 2. And again, the first row with the third row for the second determinant, and 2 multiplied by 4, it's 8, and 5 multiplied by minus 1, minus 5, minus 1 times 1, minus 1. Now this is the first row of determinant C. Now to find the second row of determinant C, we will follow the same procedure. Second row here multiplied by the first row here. 0 times 7, it's 0, plus 3 times minus 2, minus 6, and 1 times 1, it's 1. This is the first element. Now 0 times minus 3, again it's 0, plus 3 times 2, 6, plus 1 times 2 is just 2. And again 0 times 4, 0, 3 times minus 1, plus minus 3, and 1 times 1, just 1. And this is the second row of determinant C. And the third row of determinant C, 1 times 7, 7, 1 times minus 2, minus 2, 2 times 1, 2. And 1 times minus 3, it's minus 3, 1 times 2 is just 2, 1, 2 times 2, it's 4, and again 1 times 4, it's 4. 1 times minus 1, 2 times 1 is just 2. After all, the new determinant C will become 3, 2, 2, minus 5, 8, minus 2, 7, 3, 5. One of the most benefits of using determinants is to solve homogeneous equations. Now, assuming that we have the following equations. Now, these three equations are homogeneous, and we have here three unknown variables x, y, z. We would like to check whether the system here has a solution apart from the trivial solution, which is x equal to y equal to z, which is equal to 0. Now, to do this, let's create determinant of coefficient, which is equal to 5, 4, 2, 3, 2, 6, 1, 1, minus 2. Now, if we calculate the value for this determinant here, let's calculate it. D will be equal to 5 minus 4 minus 6 minus 4 minus 6 minus 6 plus 2, 3 minus 2, which equal to minus 50 plus 48 plus 2, which equal to 0. Now, this is very important here. Since the determinant is equal to 0, there is a solution other than the trivial solution x, y, and z. The point is, instead of trying to solve these equations and at the end you will get x equal to 0, y equals 0, and z equal to 0, we can double check the determinant of these equations. If the determinant is equal to 0, then it's worth it to solve these equations because you will get solutions rather than the trivial solutions x equal y equal to z, which is equal to 0. But if the determinant for the coefficient is not equal to 0, so the only solution we have here is the trivial solution, so there is no need to continue solving these equations. Now, to find the non-trivial solution, let's eliminate the z between the first, this one, and second equations. You will get here 6x plus 5y, and this is equal to 0. And upon simplifying this one here, x equal to minus 5 over 6y. Now, if we substitute this x here in the first equation right here, you will get minus 25 over 6y plus 4y plus 2z equal to 0. So minus 25y plus 24y plus 12z equal to 0. Therefore, y equal to 12z. And x in this case will be equal to minus 10z, y equal to 12z. And these values, actually x and y, satisfy the set of the three equations. Now let's have this example. For what value of lambda do the equations have the solutions other than trivial solutions? This equations here, we would like to find the values of lambda in such a way these equations will have solutions other than trivial solutions. Now let's create the determinant of coefficients 4 minus lambda 1 3 2 minus lambda, and if the system has non-trivial solution, value for this determinant should be equal to 0. So d equal to 0. Now to solve this one here, let's multiply this with this minus this with this, and the answer should be 0 in order to get non-trivial solution. So 4 minus lambda times 2 minus lambda minus 3, this equal to 0. 8 minus 6 lambda plus lambda square minus 3 equal to 0. Rearrange this one, lambda square minus 6 lambda plus 5 equal to 0. Or we can just lambda minus 5 times lambda minus 1 equal to 0. So lambda could be 5 or lambda equal to 1. Therefore, the system has non-trivial solutions if lambda equal to 5 or lambda equal to 1. Other than that, the system will have trivial solutions. So far, we discussed the solutions for homogeneous equations using determinant, and before solving the equations, we checked whether the value of the determinant equal to 0 or not. If the determinant value equal to 0, then there is a solution other than trivial solution. Other than that, if the determinant it's not equal to 0, then the solutions for the equations is trivial solution, which means x equal y equal to z, which equal to 0. Now let's discuss the solutions for non-homogeneous equations. So let's assume that a11 x plus a12 y plus a13 z equal to d1. Remember, it's non-homogeneous. a21 x plus a22 y plus a23 z equal to d2, and a31 x plus a32 y plus a33 z equal to d3. Now let's start by forming the determinants of the coefficients, then multiplying by x. X multiplied by the coefficients a11, a12, a13, a21, a22, a23, a31, a32, a33, and this equal to the determinant here. It's d1, d2, d3, and same as in this one here, because if we subtract this from this, you will get 0. Therefore, you keep d1, d2, d3 in the same column here. a12, a13, a22, a23, and a32, a33. Therefore, x times the value of this determinant, which is D in this case, should be equal to D1, D2, D3, A1, 2, A2, 2, A3, 2, A1, 3, A2, 3, A3, 3. Following the same procedure, y times the determinant d equal to, now rather than placing d1, d2, d3 in the first column, they should be in the second column right here. So it's equal to a11, this is d1, a13, a12, d2, a23, a13, D3, A3, 3, and ZD equal to, now rather than placing the D1, D2, D3 in the second column, we should place them in the third column. So A11, A12, this is D1, A12, sorry, 21, A22, D2, A3, 1, A3, 2, and this is D3. And by solving this determinant here, we can find X, and we can find Y, and we can find Z. Let's have this example. We have here three set and homogeneous equations. We would like to find X, Y, and Z. Now, before solving this, let's find the determinant D of the coefficients, which equal to 2 minus 3, 2, 4, 1, minus 1, 5, 2, minus 3. And by solving the value of this determinant, we will find D is equal to minus 17. Now, let's find D1, which equal to, remember, it's the same determinant here, but we should replace the first column, this is D1, the first column with 2, 3, and 0. So it should be 2, 3, and 0 minus 3, and the second and third column should be the same, 1, 2, 2 minus 1 minus 3. And the value for this D1 equal to, again, minus 17. Now let's calculate D2, and we should place here, rather than minus 3, 1, 2, we should place them 2, 3, and 0, and keep the determinant as is. So it will be 2, 2, 2, 4, 3, minus 1, 5, 0, minus 3, and the value for this second determinant is equal to minus 34, and last D3 equal to, we should replace the third column with 2, 3, and 0. So D3 will become here 2 minus 3, 2, 4, 1, 3, 5, 2, 0, and the value for D3 equal to minus 51. Now to find X1, remember, XD equal to D1. Therefore, X equal to d1 over d, which equal to minus 17 over 17, or 1. Again, yd equal to d2, or y equal to d2 over d, or in other words, minus 34 over minus 17, which equal to 2. And zd equal to d3, which equal to z, in this case, d3 over d, or minus 51 over minus 17. In other words, it's equal to 3. That's it. Thank you for watching.